We want to look at how can we apply the Cramers rule in the ISLM model. So now there are two things that we want to achieve by applying the Cramers rule in ISLM model. Number one, we want to use it to determine equilibrium output and interest rate. Second, we want to use it to determine how the endogenous variables in ISLM model change due to changes in exogenous variables or intercept parameters. So we want to look at the use these two applications of Cramers rule in the ISLM model. But before we can do that, we need to recall what is the Cramer's rule. So now Cramer's rule is a method that uses determinants to solve a system of linear equations that has the same number of equations as variables. So now let's look at through a numerical example, how do we use Cramer's rule to solve a system of linear equations in general, but then apply it to the ISL model after going through this recap. So we're given the system of linear equations, 2x minus 11 is minus 5y and 4 plus 3y is 3x. Now one way to go about solving it is to use substitution to find the values of x and y. But now we want to learn how can we use Cramer's rule to solve for x and y instead of say substitution. So now the first step when you're applying Cramer's rule to solve a system of linear equations is to rearrange so that the unknown variables, which in this case is x and y, appear on the left-hand side and the constants on the right-hand side of each equation. Right, so if we go back right now, they're mixed, right? We have unknown constant on the left-hand side and the right-hand side. Similarly, over here, we have an unknown constant on the left-hand side and the right-hand side. So in the first step, you want to rearrange the equations such that the unknown constants appear on the left-hand side. Sorry, unknown constants such that the unknown variables appear. So right now, so they're mixed, right? You have an unknown variable on the left-hand side, unknown variable on the right-hand side. And you have an unknown variable here on the left-hand side, similarly an unknown variable here on the right-hand side. We want to rearrange them so that the unknown variables appear only on the left-hand side and the constants appear on the right-hand side of each equation. So if we rearrange them, we get something like this. So now we've rearranged it in a such a way that the unknown variables, x and y on the left-hand side and the constants are on the right-hand side. Now, step 2 is going to be, we want to write the above model in matrix form. And the matrix form that we will use for this is AX is equal to B, where X is going to be a column vector of unknown variables. We have two unknown variables, X and Y. So X is a column vector containing X and Y. So this is X. A is going to be a coefficient matrix, where it is a matrix of the coefficients of the unknown variables. So if we go back, so we can see over here, in the first equation, the coefficient of x is 2 and the coefficient of y is 5. So then so the first row corresponds to that, right? This is the coefficient of x in the first equation. This is the coefficient of y in the first equation. And then in the second equation, the coefficient of x is minus 3 and coefficient of y is 1. So we can see in the second equation, this is the coefficient of x minus 3 and this is the coefficient of y 1. And then over here, B is our column vector of constants. Right? If we go back to equation, in the first equation, the constant was 11. So here we have an 11. In the second equation, the constant was minus 4. So here we have minus 4. So in this way, we wrote a model in matrix form where you have your column vector of unknown variables x. Here we have two unknown variables x and y. And then A is the coefficient matrix. It includes the coefficients. In the first equation, the coefficient of x was 2 and in the first equation, coefficient of y was 5. In the second equation, coefficient of x was minus 3 and coefficient of y was 1. And this is your column vector of constants. In the first equation, the constant is 11. In the second equation, the constant is minus 4. Now, the first two steps are, the first step is you rearrange them. Second step is you write it in matrix form. Now we're finally ready to apply Cramer's rule. So let's see how applying Cramer's rule, we can solve for x using Cramer's rule. Now look in this case, x is in the vector of unknowns at the first position, right? It's in the first position, x is in first position, y is in second position. So what we're going to do is, because x is in the vector of unknowns at first position, we will replace the first column in the coefficient matrix with the elements of the constant vector b. So we've created this new matrix where now the first column is going to be 11 minus 4 and the second column is 5 1. Now, Cramer's rule says calculate the determinant of the change coefficient matrix that we're calculating over here, where you can notice that in this matrix, the first column, 2 minus 3, which corresponds to x, is replaced by your constant vector b, right? And so you calculate the determinant of this change coefficient matrix and divide it by the determinant of the unchanged coefficient matrix, which is just 2 minus 3, 5, 1. Right, so this is how we can use Cramer's rule to solve for x. We see in what position is it in the vector of unknowns. Since it's in the first position, so the first column corresponds to x. So what we do is we replace the first column in the coefficient matrix that corresponds to x, because x is in the first position, with the column vector of the with the constant vector b, the elements of that. And then you take the determinant of this change coefficient matrix and divide it by the determinant of the unchanged coefficient matrix, and the result is a value of x. And this is the same value we would have solved if we had used a substitution instead. So we know how do we find the determinant of a 2 by 2 matrix? We just cross multiply and then we subtract the second product from the first. So we cross multiply 11 into 1 and then we subtract, and then we cross multiply this 5 into minus 4 and we subtract the second product from the first product. So it's 11 into 1 minus 5 into minus 4. Similarly, how do you find the determinant of this? So we cross multiply and then take the difference. So 2 into 1 minus 5 into minus 3. So this turns out to be 31 by 17. We can similarly find y using Cramer's rule as well. Now notice over here, y is in the vector of unknowns at the second position, right? X is in the first position, y is in the second position. Since y is in the second position, so the second column in the coefficient matrix corresponds to y. So what you're going to do is we're going to replace the second column in the coefficient matrix with the elements of the constant vector b. So now the change coefficient matrix will be 2 minus 3, 11 minus 4. X was in the first position, so the first column corresponded to x. So we replace that with the elements of b. Y is in the second position, so the second column in the coefficient matrix corresponds to y. So we replace that with the elements of the constant vector b. And we take the determinant of this changed coefficient matrix and divide by the determinant of the unchanged coefficient matrix. So this we just found out when finding x as well. So this remains the same because whether you're finding x or y in the denominator, you will have the denominator of the unchanged coefficient matrix. So you can just calculate it once and use that. So this we already calculated 17. The numerator is different now. So we just calculate the determinant of this. We know we take the cross product and then subtract the 2 into minus 4 minus 11 into minus 3. In this way, we can find y as well. So whenever you're using the Cramer's rule, you just seek in the vector of unknowns what is the position of that variable, and then corresponding to that position, you look at the column in the coefficient matrix and replace that by the elements of the constant vector, and then take the determinant of the change coefficient matrix and divide it by the determinant of the unchanged coefficient matrix. Something to note here is Cramer's rule can only give solutions when determinant of A is not equal to 0, because determinant of A is what we're taking in the denominator, right? Determinant of unchanged coefficient matrix A, this is A, right? So Cramer's rule only gives you solutions when this determinant is non-zero. If determinant is 0, then the system either has an infinite number of solutions or it has no solutions. We cannot find solutions using the Cramer's rule when the system has an infinite number of solutions. So we can use Cramer's rule to solve a system of linear equations where you have same number of equations as and same number of variables, but only in that case where the coefficient matrix has a non-zero determinant.